Next topic, unbalanced loads. When the loads in all three phases of either star or delta connection are not identical to each other in all respects, they are called unbalanced load. The phase currents in delta and phase or line currents in star connection differ in unbalanced loading, giving rise to flow of neutral current. Obviously, a start point in any star connection. Now, IR plus IY plus IB equals to IN, where IN is the neutral current. And for three-phase balanced loads, we know that IN equals to 0. But whereas for unbalanced load, IN is a finite value. In this context, it may be noted that when the supply, neutral, and the star point is interconnected, it is called three-phase, four-wire system. While for the absence of these connections or for supply of a delta load, the system is called three-phase, three-wire system. In unbalanced loading, due to the flow of unequal currents in each of the phase, a voltage appears at the neutral and its value can be determined as follows. The current in each phase or line being IR, IY, IB at 0, then IR plus IY plus IB equals to V RO, the voltage between R and O point, multiplied by YR is the admittance or phase, plus V YO YY plus V BO YB. Now elaborate this. V RO, which is nothing but V RN minus V ON YR plus V YN minus V ON YY plus V BN minus V OB YB. Now separate the positive and negative terms, then we are going to get V Rn Yn plus V Yn Yy plus V Bn Yb minus of V On Yr plus Yy plus Yb. From the KCL, we know that IR plus Iy plus Ib equals to 0. Then VON is given by, from this equation, V Rn Yn plus V Yn Yy plus V Bn Yb divided by Yr Yy plus Yb, where Y terms are the admittances of the respective phases. VON represents the neutral shift, that is from O to N. This is regarding unbalanced loads. Let us solve one problem. The power reading of two wattmeters are 15 kilowatts and minus 4 kilowatts. If the balanced supply voltage is 440 volts, find the power drawn, power factor, and line current. Now, from the given data, that is W1 equals to 15 kilowatts, W2 equals to minus 4 kilowatts, and the supply, that is VL, equals to 440 volts. We have the information of 2 wattmeter method that if one wattmeter is reading positive and another wattmeter is reading negative, then the power factor is going to lie in between 0.5 lag and 0, or the power factor angle is between 60 and 90 degrees. Now, the true power drawn, P, is given by W1 plus W2. W2 is minus, so minus 4, which is nothing but 11 kilowatts. Now, we have the formula that tan phi equals to root 3 times of W1 minus W2 divided by W1 plus W2. Now substitute these values. Root 3, 15 minus of minus plus 4 divided by 15 plus and minus 4. That will be root 3, 19 by 11. Tan phi equals to, now if you calculate this, you are going to get 2.99, from which phi, which is the power factor angle, is given by tan inverse of 2.99, which equals to 71.52 degrees. This is power factor angle. This is not the power factor. So power factor is given by cos of the phi value, that is cos of 71.52 degrees, which is going to give us 0.317 lag. Yeah, it is in between 0.5 lag and 0. And the angle is also between 60 and 90. Power is given by root 3 times of VL IL cos phi. We know the power. That power is 11 kilowatts, which equals to root 3 times of L is 440, and we need to find out the line current IL. Cos phi is nothing but 0.317. IL is given by 11 kilowatts divided by root 3 times of 440, 0.317. We are going to get 45.53 amps. Now the true power is 11 for A, and power factor is 0.317 lag for B, and the line current is 45.53 amps for C.